This is a profession which, if you let it, will steamroll you, right? You have so much work to do. There's always more to do in the lab. You get invitations to help with stuff. You have to, people want you to do this and this and this. For me, for example, I don't do any work typically between when I get home and when the kids go to bed, right? That's exclusively family time, no emails. I made a wonderful exception for you guys.
Hello everyone, welcome back to another segment of a series of interviews conducted by the Department of Chemistry, the Faculty of Science, the University of Colombo, where we will be interviewing eminent scientists who have blessed the scientific community with their impactful work. I am Devindu Damathage, finally an undergraduate, majoring in chemistry, and joining with me are my fellow batchmates, Havisha Hilakodipili and Devni Fernandez. Without further ado, allow me to give a brief introduction about our special guest for this segment. The scientist joining with us today deserves a greater introduction than I can possibly fit into this time limit. So he is currently an assistant professor in the Department of Electrical Engineering at Stanford University. He's a term and faculty fellow at Stanford University. He was a Moore Inventor Fellow of the Gordon and Nettie Moore Foundation. He was a Rowland Fellow of the Rowland Institute at Harvard University. He's a recipient of the Marie Curie Global Fellowship by the European Commission. He's a co-founder of Phototic 3D, a startup looking to commercialize 3D printing technologies, and has done extensive research in the fields of nanoscale, periscuit materials, single fission, and 3D printing. Over to you, Kavisha.
So, the guest we have today is none other than Professor Dan Congreve. We would like to warmly welcome you to this interview. Thank you so much for allocating your time from your busy schedule for us. We greatly appreciate it, Professor. It would be wrong of me if I don't mention your achievements, Professor Dan. You received your BS and MS from Iowa State in 2011, working with Vic Dalal, studying defect densities and nanocrystalline and amorphous silicon. Then you received your PhD from MIT in Electrical Engineering in 2015, studying under Mark Boldo, where your thesis work focused on photovoltaic energy conversion using singlet fission and triplet fusion as a down-converting and an up-converting process respectively. And you spent a year as a postdoc with Will Tisdale in Chemical Engineering at MIT studying periscuit nanoplatelets. It is definitely an honor to have you with us, Professor Dan. So, to start off today's questions, we would love to know about what you and your research team at Stanford are currently working on. Could you please share with us, Professor?
Yeah, absolutely. Thank you so much for the invitation for this interview today and for that very kind introduction. I very much appreciate it. My lab works on a lot of things, but I think what we really focus on is how can we control light and energy at the nanoscale, using particularly nanomaterials and shaping them and combining them in different ways to solve challenging applications. And these applications can range over a pretty wide spectrum, and I'll touch on a couple of them here. But I think really the heart of what we do is engineering those nanomaterials, understanding how energy and light can flow between them, how we can put energy in and get energy out, and just engineering them to be more efficient and to do things that are perhaps unexpected when we talk about things like up conversion in particular. And so we do a lot of research on optoelectronic devices, including solar cells, light emitting diodes, and lasers, looking at new materials to build those systems out of to make them more efficient, more stable, have better color properties, access other wavelengths, all sorts of fun stuff like that. We also look and really enjoy working with a process called photon energy conversion. So either converting low energy photons to high energy photons, so 2 low energy photons, 1 higher energy photon, or 1 high energy photon becoming 2 lower energy photons. And it turns out if you can do these processes efficiently, they have really remarkable applications for making more efficient solar cells, making it easier to interact with biological materials for 3D printing, anti-counterfeiting, night vision, all sorts of fun stuff like that. So we like to really play with these processes to understand them and manipulate them to build new and exciting devices.
Thank you, Professor. That's a really interesting answer. So as my second question, Professor, would you be able to talk a bit about your childhood, what inspired to choose electrical engineering as your profession, and what drove you to work hard to be at the position that you're at today?
Yeah, absolutely. So, I didn't target electrical engineering from a very young age. I just knew that I really enjoyed working with math and doing experiments from, the early days of building, model trains and building things with my hands and all sorts of stuff. And so as I got advanced through school, I really enjoyed my math classes and I really enjoyed my science classes. And so I continued to work for them over time. And so by the time I went away to college, I became very attached very quickly to the engineering college at Iowa State University, where they give you this really cool opportunity to interact with different disciplines of engineering. So I met with chemical engineering, aerospace engineering, material science, all of these different disciplines of engineering. And something about electrical engineering really stuck with me. And so I chose that as my major in undergrad. And so what I really found was that they did so many cool things that you do in electrical engineering, from kind of information theory and algorithms all the way to hardware, software systems and designing of chips, all the way to physical systems, which I tend to be on the side of device physics and nanomaterials and all sorts of stuff like that. And so as I advanced through my career, within that fairly large spectrum, I moved around a lot, kind of just chasing things that interested me, right? So my master's work was on defect states in amorphous crystalline solar cells. So taking these amorphous silicon solar cells, taking them and measuring their defect states and correlating that with device performance. And then I switched and started working with organic photovoltaics in graduate school, and exploring new material systems and new opportunities, leading to some of the cool things, or at least I think they're cool, that we do today that aren't necessarily related to those topics, things like the 3D printing and stuff like that. So really, it's been a long path of looking and identifying topics and material systems and processes that we think are interesting, and just sort of looking for new opportunities and where we can use our skills to do something interesting.
Okay, thank you, Professor. I hope our young viewers are much inspired by your answer. So, Professor, as my next question, I have observed your research team works on exploring and utilizing a variety of nanoscale periscuit materials. Could you please explain to us what nanoscale periscuits are and how does it link with light emission?
Absolutely. So perovskites in general are a class of materials. They're a material system that takes a particular chemical formula and has a particular crystal structure. And it turns out there's actually a ton of these materials that take this particular form. But we tend to be interested in one specific subset of these, which are often called lead halide perovskites, because one of the materials, one of the atoms that makes them up is lead, and another is a halide, either chloride, bromide, or iodide. And these materials have been around for a long time, but they've really taken off in the last 10 years or so because they were recognized as really, really remarkable optoelectronic materials. And especially this started sort of for solar cells, where they are now, I would argue, one of the most exciting solar cell technologies on the planet today. But it turns out they're also really good light emitters. And we can talk a little bit more about the properties that have them, that make them that way. But really, one of the things that's most exciting is that you'll notice I didn't specify a particular halide when I described their structures. Like, you can put in chloride, you can put in iodide, you can put in bromide. And what's really interesting and really cool is that depending on which of those you plug in, you can change the color that it emits. So if you put in just chloride materials, it'll emit right at the violet edge of the spectrum, like purple, deep purple. If you put in just bromide, it emits green. And if you put in just iodide, it'll emit in the near infrared. So you can do mixtures as well. You don't have to just pick one. You can do part bromide and part chloride, for example. And so you can adjust the ratios of these ions in the material and literally make any emissive color across the visible spectrum that you want, which means this is a really exciting material platform for things like LEDs, where getting a particular color for something like a phone screen or a TV or something like that is a really, really important deal. And so we really like these materials for their tunability. Now, you asked specifically about nanoscale materials. And what's interesting about these materials is that you can really kind of shape and sculpt them in many different ways at the nanoscale. And when you do that, it changes the property of the material in really interesting ways. So, when you typically make a solar cell, these are fairly bulk thin films. So it's fairly large crystals of the material, polycrystalline thin films. But you can also take and you can make this material basically zero dimensional, otherwise known as a quantum dot often, where the material is just a couple of nanometers on any side, maybe high single digits, 7, 8, 9, 10, up to about 20 nanometers or so, surrounded by organic materials that keep it nice and small and soluble and does all these good things. And when you do that, you can make it a lot brighter. These tend to have very high emissive efficiencies. And you can also work with them easier. They're very solution processable and lots of fun things like that. People have also figured out how to make nano wires. So one dimension, very small in 2 dimensions and then long in 1 dimension. So literally nanoscale wires, or what are called nanoplatelets or layered perovskites, which is basically, imagine sheets of paper of a perovskite material, as well as these bulk films. And depending on which form you put it in, different and exciting things happen. And so we really like to play with the different forms that we have available to us to try to meet particular goals and particular aims. And so it gives us a lot of flexibility and a lot of tunability to play with these material systems and to understand how they work, why they work, how we can make them better, and how we can then translate that to an emissive device, whether it's an LED or a laser, or translate it to something like a photovoltaic device or something else along those lines.
Thank you very much for the detailed answer. So, Professor, you have been able to build the Congreve lab at Stanford to better understand the physics behind nanoscale materials and apply that knowledge into building more efficient devices like LEDs and photovoltaics. How do you feel about this and being able to carry out research experiments with students at Stanford?
I love it. The people here are really amazing. Don't tell them this, but my students are absolutely the best, right? I don't want them to get too big of a head, so don't tell them this. But they're really just wonderful people to work with, and they come up with all sorts of creative and interesting ideas of new things to try. And the same with everyone else here at Stanford are just really wonderful people to work with, not only in terms of their understanding of different sciences and of their field, right? They're all very smart people, but also they're just really good people to work with, and that they're very good collaborators. They're very kind. We really enjoy hanging out at them. So I've really enjoyed our time at Stanford, and I'm really excited about the research that we're doing and the group that we're building, and hopefully we'll have some exciting things happening over the coming months and years.
All right, Professor, let me ask you about a little bit a longer question.
Yeah.
One of your latest research interests focuses on a new and improved method of 3D printing that could make it easier to print increasingly complex designs while saving time and material. What made you interested in this field? How will the research you and your team are working on improve the existing technologies for 3D printing? And what do you believe is the future of 3D printing and how it would shape our futures?
That's a big question. Yeah. So, what got us interested in this field is an interesting story in that it was almost entirely accidental. It was not designed we didn't sit down and be like, we should definitely move into 3D printing next. Obviously 3D printing is a really fun field, and we've been, I've played with 3D printers my whole life. It's a lot of fun to print little things and play with them and all of that stuff. But actually, we weren't developing materials for 3D printing at all. We were trying to develop, and still are, develop materials for biological interactions. So materials that could do this up conversion process where you can absorb low energy photons and emit higher energy photons, and apply that process, basically have that process occur safely and efficiently within biological tissue. And so to do that, what you have to do is basically take your up conversion media and surround it with a protective shell, and then put a coating on it to help it be soluble and all sorts of things like this. And so we spent a lot of time developing these nanomaterials. And one day we just sort of came to lab while these materials were sort of half developed, I would say at the time. It took us a long time to get them right. We just said, are these materials of interest, not just for this bio interaction that we've been aiming for, but what about for 3D printing? And I asked my postdoc at the time, Sam Sanders, I said, just imagine they work beautifully. What could we do with this for 3D printing? I was like, put a presentation together, show it at group meeting next time, and we'll just brainstorm. And so Sam and Mahesh and I went in a room at group meeting the next time. My group was small at the time. And Sam presented this, and we're like, oh my God, this could be really cool and really interesting and really useful. And so we made the decision to pause our work on the biomaterials and instead to focus on the application of these materials to 3D printing. So why does this research matter? What did Sam tell us that got us really excited in that meeting? Well, basically, normally when you do 3D printing, you actually do 2D printing over and over and over again. Right? So if you've played with a 3D printer, you print a layer, and you can print this in a lot of different ways. You can pattern it with a laser from beneath. You can have a head move around and extrude material, whatever it is. And then you lift this layer up and you have fresh resin flows in underneath. Now I'm doing the laser example. You put this back down, pattern it again, pick it up, fresh resin flows in, put it down, pattern the resin. And if you do that, 1,000 times, you have your 3D printer going. These are just amazing machines, right? We have a Form Labs in my lab, which we love and we use all the time. But that layer by layer nature really introduces some challenges, especially regarding the nature of support structures, the requirements it puts on the resin, stuff like that. And so what you would really want in a perfect world from a 3D printing perspective is the ability to sort of take a vat of resin in 3 dimensions, like a Jello cup or something like that, and just pattern it all at once with light or with a laser and be done. And it turns out that's really hard to do, because to pattern a point, if you imagine a Jello cup and I said, hey, can you cure a point just in the middle of that? That turns out to be a really big challenge, because if you shoot a laser in, it's going to cure all the way down the path of the laser, cure the middle, and then cure the path of the laser as it comes out as well. And so this typically not been something that's been actively done. But now what we figured out is that we could use this up conversion process to do the same thing. So if you focus the laser beam, because up conversion depends quadratically on the intensity of light, you get a little bit of blue up conversion only at the focal point of the laser beam. So if you take that same Jello cup and you focus a red laser beam, the red laser beam does nothing to the resin. You'll get a little pinprick of blue light at the focal point of the laser beam, and then just red all the way through. And we have pictures of this in our paper. And so that blue dot then can couple with the photoinitiator and the resin, cause a little bit of curing, and then you scan that thing around in 3 dimensions, and you have your 3D print. It's really great. I do want to highlight that this is just one of several new what's called volumetric 3D printing techniques that have come out. There's been lots of cool work from a variety of groups that are probably now 4 or 5 different methods of volumetric printing. It's all very exciting and a lot of fun. So, that's the research that we're working on and the improvements that we're striving for. The future of 3D printing and how it shapes our future is a very big question, I think. But, I'll suffice it to say that I think it's a very exciting time, because one of the things that 3D printing has aimed to do for a long time is to transition from sort of a prototyping regime, where you basically use it to build prototypes, and then you figure out a different industrial manufacture when you want to make, 1 million of something, right? To actually doing that manufacturing process where you can have mass customization, very fast speed, better utilization of materials. And I think with all of the different technologies that you're seeing develop, both in academia as well as at a whole bunch of really exciting companies, I think that transition is starting to happen. And so I think 3D printing is going to be an increasingly important part of our not only just our prototyping world, but our manufacturing world moving forward. It's something that's very exciting, and I'm super happy to play a very, 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 very small part of going forward.
All right, Professor. Thank you for the detailed answer. And my next question is, Professor, you are the co-founder of a startup focused commercialization of 3D printing. Can you tell us about your experience, about your entry to the business side of science as a science entrepreneur, the challenges you faced, and any advice regarding this element of being a scientist?
Yeah, absolutely. So as you mentioned, I'm a chief scientific advisor and a co-founder to a startup developing some 3D printing technologies. And this was spun out of my lab while it was still at Harvard. The company is still based in Cambridge, Massachusetts. And it's been a really interesting process going through this, because it's very different than a typical scientific development. So it's been really illuminating to see this process going on. And I think the big difference to highlight here is just the difference in time scale and the difference in scope. So a lot of times when we're dealing with academic questions, we're looking at things that are, maybe 5 to 10 years away, maybe even longer in some cases for fundamental science from hitting the market, right? If you look at things, the LEDs that we build, right? Those are at least 5 to 10 years away from being seriously commercialized. And I think other fields are often very similar. And that's a really great thing in academia. But as you make that transition to a commercial company, what you typically find is that time horizon is much shorter. Typically, when you raise money in a startup, it's often a year, maybe 2 years, and then you have to raise money again, which means you have to prove that you've done something impactful in that time. And so that time horizon really changes the way that you think about the product and the way that you focus on what you're doing. So you're a lot more focused on one particular thing and trying to execute that and move forward through it. And so what I would say is that it's been really interesting seeing that dynamic at work and seeing that at play. And it really takes sort of a special confluence of events, I think, to make a productive and a successful start. I mean, we're not successful yet. We're still working very, very hard at it. And I think it takes as I said, a special combination of things. Not only do you have to have a really cool idea, which I think, a lot of academics have really cool ideas, but it has to fulfill a particular market need. And it has to, you have to have a leadership team ready to go, meaning you have to have someone who would be a good, capable leader of that startup ready to lead the lab and go do that, whether that's the PI or the student or whoever it is. And so it's this complex combination of science and technology and market and people that have to kind of all come together at the same time to be really successful. And that's been really fun to watch occur in real time. And I think in terms of advice for scientists, I think because it takes all of these different things to come together, I think it's difficult to sort of come in and do research with an aim of turning that particular research goal into a startup, right? So you can't just come in and be like, I'm going to work on, perovskite LEDs and I'm going to get really good at them and we're going to spin the tech out of the lab and found a startup, right? I think that type of goal is very difficult to achieve. But if you're really interested in startups, I think one of the things that you can really do is to really refine that innovative skill and approach several different projects, try different things, talk with people, learn to evaluate not only the sort of technical aspects that we think so much about in academia and correctly so, but also be able to evaluate the market impact of some of those things and evaluate where the market opportunities are and just meet with and interact with as many people as you can to really just be looking for those opportunities and to identify them so you can move around and potentially go work with new people as needed to sort of drive in that direction. So it's a really exciting and innovating field, and I'm just really enjoyed being a part of it so far.
Thank you very much, Professor, for that answer. So we have noticed that Singlet fission has been one of your early research interests, which is something my research supervisor and I myself is quite interested in currently doing research on it. So could you tell us about your experience working in this area, your opinions on it as a future application for photovoltaic devices, because we talked about photovoltaic devices a lot, and what eventually made you put that side of research into halt?
Yeah, absolutely. So Singlet fission is a really fun and interesting process. For those of you not familiar with this on the call, this is the ability to take one higher energy photon and split its energy into two lower energy photons using excited states in molecules. And if you can do that, you can make solar cells substantially more efficient by basically getting a free electron from every high energy photon. If you do that, if you do everything right, you can make substantially more efficient solar cells. And so it's a really exciting technique. I worked on it for years throughout my graduate degree, starting working on organic solar cells, and we were able to show quantum efficiencies that were substantially over 100%, showing that you can sort of do this process very, very efficiently in solar cells. And two really awesome graduate students in Mark Baldo's group after I left, Tony and Marcus, were able to show that this you actually could take these resultant excitons and transfer them to a silicon solar cell, and so harvest them in these sort of very high efficiency ways. That's been very exciting work as well, and a completely very challenging project. So a hat tip to Tony and Marcus for working really, really hard on that. And so this has been a really exciting process. And why did the research come to a halt? I don't think it actually had anything to do with singlet fission itself. It just merely had to do with my career stage evolving. First, as a postdoc, I went to work on something different. And then I started as a roll-in fellowship and only had a very small lab. And so, could only have very limited hands in the type of targets that we, or the type of applications that we targeted. But I will say, I think that opportunities are ripe for that field to continue. One of the things that we were waiting for, right, is proving that this process could have a high power efficiency benefit. So that seems like I'm kind of splitting hairs of talking about the difference between quantum or counting efficiency and power efficiency. But it turns out that's actually really, really important. In this device that we showed where we're getting quantum efficiencies over 100%, the power efficiency was only about 2%. And that's to compare with something like silicon, which can be upwards of 22, 23, 24%. And so to get around that challenge, you need we felt at the time you needed substantially new materials to work with, right? Whether that was coupling this to silicon, doing all optical down conversion or something else. And what we've seen over the last 5 or 6 years is the development of a number of exciting material systems, not the least of which is perovskites, but also, wonderful development in organic photovoltaics, and as well as looking at things like passivation of silicon. These sort of enhancements in these technologies, I think, are starting to open the door for the investigation of this technology to be renewed. So I think there is still a lot of life left in this process, and hopefully we will get to play a role in figuring that out as things continue to move forward.
Thank you, Professor. So I came across a list of awards and award that had been offered to you as an appreciation of your achievements to the scientific community and the world. So we would like to know which one of them is the most valuable to you. Like, is there a story behind it? We'd love to know it, Professor.
Yeah, each award is really special because it represents some different aspect of work that you've done or contribution that you've made or something like that. And I think for me, the one that's really special is the Moore Inventor Fellowship. I won this about 3 years ago in 2019. And the reason that it's special is that it's part honorific in terms of the award that you win of having this cool invention and trying to drive it forward. But it also came with really substantial training about how to translate ideas from lab to industry and discussing that. So we actually meet as fellowship groups once a year and discuss our experiences. So it's helped me to build a network of similar career stage inventors. It's given me training on how to approach some of these challenges and these problems. And overall, just been it's a really nice honor to have, especially being here in Silicon Valley. To be associated with the Moore Foundation is very humbling, but also helped me to continue to develop my skills moving forward. And so for that, I'm very, very appreciative to the Moore Foundation for the rest of my career. Everything I've learned will continue to be useful as I move forward. So I think that has a particularly special place in my heart.
Thank you, Professor. So as a prominent scientist, I'm sure you're loaded up with work and various responsibilities. You're an assistant professor, you're an entrepreneur, and you're a father. So how do you balance your work life with your personal life? Because we are struggling, even though we don't have personal lives as much as you, to maintain a balance with our studies and other aspects of our life. So what advice would you give on that, Professor?
I think the key is, especially as things get busier, is to make very active decisions and to not let things just sort of happen to you, right? And so if you listen very carefully, you can actually probably hear Bluey playing in the next room that my kids are watching after dinner. Bluey's fantastic, by the way. I could talk about that for hours. But anyways, and if I took the computer and turned it just a little bit this way, you would see the train tracks that my son was building earlier this evening, right? And so it becomes very tied together. By the way, I have a 4-year-old and a 2-year-old, 4-year-old and 2-year-old kids. And I think the key, especially in a profession like academia, the key is to just be very clear with yourself about what your priorities are, and to really go and make conscious decisions as you try to execute them, right? This is a profession which, if you let it, will steamroll you, right? You have so much work to do. There's always more to do in the lab. You get invitations to help with stuff. You have to, people want you to do this and this and this. If you let it, it can steamroll you. And that's true at all career stages. But, when I was in graduate school, I was a little happier to just, go into the lab at all hours of the night and try different experiments and stuff like that. And so you have to be very conscious about making your decisions and your priorities of what's important. So, for me, for example, I don't do any work typically between when I get home and when the kids go to bed, right? That's exclusively family time, no emails. I made a wonderful exception for you guys for this interview, but normally that, and on weekends, other than when the kids are asleep, I'm focused on family time exclusively. And so it's about finding that prioritization and also finding efficiency, right? I think you're going to ask a general advice question. One of the most important advice I have for people is to find and to make efficient use of your time, right? And I think in science, a lot of times we think about like how many hours we worked. We think about it, hey, I was in lab for 70 hours this week, or whatever the number is. And we use that as our metric. But I think we often forget about how do we get the most out of every single hour that we're in lab. And so having kids, having a family, having all of these other obligations really focuses you down to making sure that every hour you spend in the lab or at work are efficient hours that you're getting the most out of. And so I think that's the other part of it, is taking those hours that you do have and making sure you're efficient with them, making sure that you're not just, surfing social media or just, chatting with people all the time or sort of staring off into space. I mean, you need to do a little staring off in space in science while you process your ideas and your results, but just making sure that you get the most out of those hours. So those are kind of the two things: to make active decisions, to say, this is important to me, so I'll do it. This is not important to me, so I'm not going to do it. And not letting the profession steamroll you. And then also with the hours that you have, making sure that they are efficient and productive.
All right, Professor, thank you for this answer. And my final question is, what would be your advice to young undergraduates like us who are passionate about science and would like to pursue a career in science, and also are in hopes of working under scientists like you and taking part in impactful research?
Yeah, absolutely. So I have a list here that I try to provide to people when they want to know this thing. So I hope you guys won't mind me working my way through a list. The first is to find an environment where you will be successful. Okay, and I talk about this a lot when people talk about selecting research groups, selecting schools to go to, something like that, is that you really want to pay close attention to the group that you're joining, the school that you're joining, whatever it is. You want to find that environment that enables you to be the best researcher that you can be. And for each of us, that means something a little bit different, right? Some people kind of like to just be left alone and have available, chat in every once in a while. Some people like very active check-ins from their supervisor, very collaborative group cultures. Each of those are totally fine, but it's just important to know which one you are and find a group that matches accordingly, because science is really hard, right? Science is a very difficult profession. You're usually failing. Most experiments fail, most grant apps fail, most paper submissions are rejected on the first try, right? Science is a really big pile of failure. And so you want to find that group that you can kind of support you as you transition through all of these things and to get out of bed and to try your experiment again. So number one, find an environment you can be successful. Number two, and we kind of talked about this already, so I won't belabor it too much, hard work really matters in this profession, but it's not everything, right? And you really want to take the time to think about what you're doing with those individual hours, and also making sure that you're not burning yourself out. If you work really, really hard for 2 weeks, but then are burned out and need 3 weeks of rest to require from that, that's not a productive use of your time, right? Much better is to find a sustainable method of efficient hours and time off that works for you. And it's different for all of us. And so you have to find out what that balance is that works for you. The next is to learn to communicate your science. This is a big one, right? Is no matter how cool the thing that you do is, if you can't communicate it clearly and in a way that other people can understand what you're doing, it doesn't really count, right? And this is written communication, this is verbal communication, this is formal, standing up in front of people and giving a presentation, but it's also informal, chatting with your advisor for 5 minutes in the hallway, right? And being able to have that ability to communicate clearly what you've done, why it matters, why it's important, the next steps that you're taking, all of those things are crucial to your scientific career as you go forward. Next, explore opportunities widely, right? Take advantage of all the wonderful resources that you have at your school, any future schools that you might go. There's tons of really intelligent, really smart, really interesting people, really cool programs, all of these things to take advantage of. So make sure that you're exploring them as much as possible. The people next to you are going to be the people leading science for your entire generation. And so get to know them, get to learn from them. Maybe they'll get to learn from you as well, and just build those connections. Next, learn to fail and embrace failure. Like I said, science is hard. You're going to fail most of the time, and that's okay, right? It's really important to keep moving forward when you fail. A lot of when I see graduate students struggle is because they failed and they're having trouble going in and trying again. So you have to develop that perseverance to keep going at your experiment, to keep trying, to try new things, try a new approach, think about a new approach, and keep pushing through even when it's not working. That perseverance, I think, honestly, is probably the most important thing to success in science, more than some arbitrary notion of intelligence or anything like that. Really, perseverance is the thing that you're looking for, I think, more than anything else. Watch out for imposter syndrome. This is something that strikes really nastily in science, where you feel like you don't belong, or you were chosen incorrectly for a position, or that everyone around you is just so much smarter. Why are you even here? Watch out for it. It's all over in science. It's really nefarious. And if it gets into your head, it's very difficult to get out of your head. So be aware of that. Watch out for it. Talk about it with your peers, and just be aware that that's something that happens. And finally, last one, reach out to people, right? Don't be afraid to be the instigator of a communication, to send an email to that person you have a question about, to go to an office hour for a faculty just to ask them about their research, to stay after class and ask if you can have a research position in your lab. There are so many wonderful people out there, but oftentimes, sitting around waiting for them to come to you is not going to work. Go to them, reach out to them, ask them questions, send an email, meet with them in their office hours, ask interesting questions, go to a seminar and ask a question, right? Like that can feel really intimidating, but go to the seminar, raise your hand, ask a question, go up afterwards and ask another question, right? Really push yourself to reach out to those other people. All right, so that's my list. It's certainly non-exhaustive, and there's lots of other things as well, but I think those are the things that I really like to highlight, that if you can really work on improving those in yourself, you'll have a successful undergraduate, graduate, whatever, through academia. You'll have a successful academic life.
Thank you so much, Professor, for that wonderful answer. And now we reach to the end of our meeting. Thank you so much, Professor Dan, for this wonderful interview you gave us and for allocating time for us from your busy schedule. We are very grateful and honored to be able to be in your presence, at least virtually, and listen to your experiences, advice, and wisdom. I would also like to thank the coordinators of this activity for making this once in a lifetime opportunity possible for us. It was a great learning experience for us. It's now time to wrap up this segment, and I would once again like to thank Professor Dan Congreve for accepting to participate in this interview. Hope you all stay safe and productive. Thank you for tuning in. Goodbye.
Thank you so much.